All right. Hello, everyone. Happy New Year. Best wishes. It's a pleasure to start the distinguished seminar in Optimization and Data series with Robert Schapire, who's a partner researcher at Microsoft Research. Rob received his PhD from MIT in 1991. And after a short postdoc at Harvard, he joined AT&T Labs. And then in 2002, he became a professor of computer science at Princeton University. In 2014, he joined Microsoft Research. Rob made many superb contributions to machine learning research and beyond, and received numerous awards, including the Gödel Prize and the Kanellakis Prize. He's a member of the National Academy of Science and the National Academy of Engineering. And today he's going to present work related to his new book, co-authored with Miro Dudik and Mateusz Telgarski, on convex analysis at infinity. This is an invitation to enter a new world of duality, conjugacy, subdifferential calculus. And it will be followed on Wednesday by a topical workshop with more advanced lectures. After the talk, Miro Dudik will join him on stage. Thank you, Rob. The stage is yours.
Thanks a lot. Thanks for that introduction. Thank you so much for inviting me. As Zaid said, I'm going to be talking about astral space and convex analysis at infinity, joint work with Miro Dudik and Mateusz Telgarski. And this is going to be published as a book, hopefully appearing in the fall. And so, but there's a preprint available, a final draft available on archive at this URL. Okay, so this talk is about convex functions and how to minimize them. And I'm sure I don't need to tell people that minimizing convex functions is a very important problem, and it's the basis for all kinds of techniques in machine learning and statistics and lots of other fields. It's used for things like maximum likelihood, maximum entropy, linear regression, logistic regression, boosting, support vector machines. The list goes on and on. And convex functions are just really nice to work with. So for instance, a local minimum of a convex function is always a global minimum. And if the gradient at a point is 0, then that point has to be a global minimizer. And it's just usually easier to find and analyze minimization algorithms. I mean, look at this function. How hard could it be to minimize that, right? And they just have beautiful, beautiful properties. So in studying convex functions, it's common, it's not universal, but it's common to assume that the function that we're trying to minimize actually attains its minimum at some finite point, like this function here, this parabola. But the problem is that some convex functions have no finite minimizer. So this is the exponential function, which I'll talk more about on the slide. And even for that simple a function, there's no finite point where the function attains its minimum. And so instead, a function like that can only be minimized by a sequence as that sequence heads to infinity, or in this case, as the sequence goes to negative infinity. And this includes cases of practical interest. So for techniques like boosting, this is not an unusual case. This is actually the typical case. So it certainly can happen in practice. And when it happens, analyzing the convergence of optimization algorithms can be more challenging and often requires more carefully tailored techniques. It's not that it's impossible, but it's more challenging. So what we're trying to do in this work is to develop a theory for studying those minimizers at infinity. So to make it more concrete, let's look a little bit more closely at the exponential function, which I'm showing here, e to the x. And as I already said, there's no finite point where the minimum of that function is attained. So instead, the function can only be minimized by a sequence of points that head to negative infinity. And we wish we could say that the function is minimized at negative infinity, because intuitively that's what's happening. It's minimized at negative infinity. And mathematically, there's a way we can do that. What we can do is we can take the real numbers and we can extend them to include plus or minus infinity. So the new set is called the extended reals, and it's written r bar. And again, all it is the real numbers together with plus and minus infinity. And then we can take this function, the exponential function that we're interested in, and we can extend it to the extended reals in kind of the natural way. We just let it be equal to 0 at negative infinity and plus infinity at plus infinity. And so if we extend this function in this way, it's got some nice properties. So first of all, it's continuous over the extended reals. Also, it attains its minimum at negative infinity. So whereas the original function did not attain its minimum, this function does attain its minimum. And the function kind of feels convex. So in standard convex analysis, there's not a way that I know of to define convexity for functions defined over the extended reals, but this function certainly feels convex. And it also feels like maybe we could extend derivatives in a natural way so that the derivative at negative infinity would be equal to 0. And then we would maintain this property that for convex functions, the minimum is attained at points where the derivative or gradient is 0. So if you're just working in one dimension, everything seems pretty straightforward. It seems pretty clear how we can add these points at infinity and how we can extend functions to this enlarged space in a way that captures those minimizers. But what happens in 2 or more dimensions? In 2 or more dimensions, things change quite a bit. So the goal of this project is to take Euclidean space, n-dimensional Euclidean space, and extend it to include these points at infinity. So what we're trying to do is we're aiming to reveal the structure of how convex functions behave at infinity. And we're trying to build up foundations in the same way that convex optimization is built on convex analysis. We're trying to extend the foundations of convex analysis so that it'll be relatively easy, or at least easier than it is now, to prove convergence of algorithms, even when the function we care about has no finite minimizers. And we're hoping to make the study of convex functions more complete, so that, for instance, every convex function can be, when it's extended to this space, has a minimizer. And we're trying to do all this in a way that will be compatible with the key notions of convex analysis. Okay, so to try and get a feeling for what we're trying to do, I like to make an analogy. So just imagine that you're living in the time of Pythagoras and that you only know about the rational numbers. Okay, so in Pythagoras only knew about the rational numbers. And if that's all you know about, and you want to figure out the length of the diagonal of a unit square of a 1 by 1 square, you have a problem. I mean, now we know, of course, that that diagonal is square root of 2. But if all you know about are rational numbers, then there's no number, no rational number, which is equal to that length. So instead, what you could do is you could approach that value of square root of 2 with sequences of rational numbers. So like here are 2 sequences of rational numbers that both converge to square root of 2. The first one was actually known to the ancient Greeks. The second one was is just based on the decimal representation of the number. And so, in a sense, we don't really need the real numbers. In a sense, we could just do all of mathematics by working over these sequences of rational numbers. But of course, that would be insane. It's clearly much more preferable to take the rational numbers and extend them to the real numbers, because then you end up with this set which is much more complete and well structured, and in which these real numbers can be treated as mathematical objects in their own right. So in the same way, we could continue to use sequences to study the minimizers of convex functions. That's what we do now. We don't give those minimizers names. Instead, we just work with sequences. But maybe it might be nicer to study those minimizers at infinity as mathematical objects in their own right. And we can hope that this bigger space will be more complete and more revealing of structure. That's the hope. Okay, so in this work, we introduce what we're calling astral space, which is an extension of Euclidean space to which these points at infinity have been added. And we also show how to extend functions which are defined on Euclidean space to astral space, to this larger space. And we study key properties and topics extended to astral space, especially topics from convex analysis. So we're really trying to extend convex analysis itself. Okay, so here's an outline of the talk. So I'll start by talking about looking at some examples of what these minimizers at infinity can look like. Then I'll talk about how to construct astral space. We'll look at what astral points are like. And then we'll talk about how to extend functions to astral space. And hopefully there will be time to talk a little bit about convergence of iterative algorithms. Okay, and feel free to interrupt me also. Okay, so before I dive in, a little bit of notation. So I'll always be using n for the dimension of the space we're working in. So we're in n-dimensional Euclidean space. I'll be denoting scalars, so that is points in R, real numbers, just in italics like this, x, y, and so on. Vectors, which are, in other words, points in Rn, Euclidean space, are indicated in bold, like x, u, v. So in particular, a tuple like this vector x has components x1 through xn, which are not in bold because they're scalars. All sequences in this talk are always indexed by the letter t. So t is the index of all sequences. And so that means that limits and convergence in this talk are always as t goes to infinity. And then I use this notation xt with parentheses to indicate a sequence. Right? Okay. So what can minimizers at infinity look like? So given a convex function f, and so this function is defined on Euclidean space, Rn, and as is standard, this function can take values which are either real or they could be plus or minus infinity. So as I said already, if there's no finite minimizer, we can only minimize that function with a sequence as it goes to infinity. So what can those minimizers at infinity look like? So in one dimension, it can only converge to plus or minus infinity, as we saw already. But in two or more dimensions, there are many, many more possibilities. So let's look at some examples. So here's an example function in R2. So it has two variables, x1 and x2. And this is the function written out algebraically. And here's a plot of the function. So the top part is showing just a surface plot of the function, and the bottom part is showing a contour plot. So if you haven't seen a contour plot, it's like a topological map if you're going hiking or whatever. So each one of these curves is showing where the function, the points where the function takes a particular value, like where this function is equal to 3 or something. Okay, so you can see for this function, that this function is like the back end of a canoe. And to minimize this function, what do we need to do? Well, to minimize the first term, we need to drive this first term, this exponential to 0, we need x1 to go to infinity. And for the second term to go to 0, we need x1 and x2 to be asymptotically equal. So we need their difference to go to 0. So for instance, we could minimize this function with a sequence like this, where we just let x1 and x2 be equal to t, and let t go to infinity. So that would give us a sequence, we could write that as xt, the pairs t comma t, and so on. So here they are, 1, 1, 2, 2, 3, 3, and so on. So this sequence is just following this diagonal valley to infinity. So the point is that it matters how the sequence goes to infinity. So direction matters. So if we head off in a different direction, then we won't be minimizing the function. And offset also matters. So if you just take that same sequence and you move it over by a fixed offset, it also won't minimize this function. So it matters how you go to infinity. Okay, so in that example, the function could be minimized by following a straight line to infinity. So is it always the case that every convex function can be minimized along a half-line? And so Jamie is shaking her head no. So here's an example of such a function, which is sort of similar, a sum of two exponentials like this. And to minimize this function, well, to minimize the first term, we need x1 to go to infinity. But to minimize the second term, we also need x2 to go to infinity. But it has to be going to infinity much faster than x1 is going to infinity, so that this exponent will be converging to minus infinity. So for instance, you can minimize this function by following a parabola to infinity with this sequence of pairs t comma t squared. Okay, and it's possible to show that there's no sequence which minimizes this function along any half-line by following a straight line to infinity. Okay, so how can we construct a space that captures these such minimizers at infinity? Okay, so that brings us to the next part, how to construct astral space. Okay, so these kinds of sequences to infinity, they don't converge because there's nothing out there for them to converge to. There's nothing at infinity for them to converge to. So the idea is to construct a space by adding new points to Euclidean space so that those new points will be the limits of those kinds of sequences. That's the idea. So how do we do that? Well, to do that, there are two basic questions we have to be able to answer. So the first question is, which sequences should have limits? So which sequences should have limits? And secondly, when should two sequences have the same limits, same limit? And if we can answer both those questions, then we have a way of constructing this space. Because what we can do is we can add new points to be the limits of all the sequences that are supposed to have limits. And then we can do it in such a way that we're effectively just adding one new point to be the limit of every group of sequences that are supposed to all have the same limit according to this second criterion. Okay? So that's the idea. So the key step here is to figure out how to answer these questions. So to see how we answer those questions, let's look at some examples. So first of all, which sequences should have limits? Well, I won't fully answer that at this point, but I think it's fair to say that just a ray that just follows a straight line to infinity should have a limit. Okay, so here's just a sequence that's following a ray, a straight line to infinity, and here it is algebraically. And so it should have a limit. when we construct this space. So what sequences should have the same limit as this sequence? Well, there's some obvious ones. So like if you just change the rate at which this sequence is converging to infinity, then it should still have the same limit, clearly. But here's a less obvious question. So suppose we take that sequence that we had and we just shift it over by a fixed offset to end up with a sequence like this blue one, okay, which I've shown down here algebraically as xt prime. So these two sequences should have limits, but should they have the same limit? Should they converge to the same point or not? So you could answer this question either way. You could answer this question either way. But we think that the answer should be no, because offset matters for minimization, as we saw in one of those examples. And because in applications, the kinds of applications that we care about, we often do care about these kinds of offsets, not just the overall direction of minimization. Okay, so how can we capture these intuitions? So in this work, we adopt a basic principle. The basic principle is to focus on the limits of sequences in every direction u, in every possible direction u. In other words, along all possible one-dimensional projections of the sequence. So let me show you what I mean by that with an example. Okay, so here again are these two parallel sequences, okay, just as before. And now we want to determine whether these two sequences should have the same limit. So what we do is we consider different possible directions of projecting these sequences. So for instance, first we might start with the vector 1, 0, which is defining a direction along this x-axis. And then we can take the first sequence and just project it down along a line parallel to that vector u. And mathematically, all we're doing is taking the inner product of each element with u, which converges to plus infinity, and you can see it in the picture too. And then we do the same thing with the second sequence, and that second sequence also converges to plus infinity. So far, these two sequences are behaving the same. But of course, we need to consider all possible directions u. So let's pick another direction u, like this one. So in this direction, if we take the sequences and project them down along this line parallel to this vector u, then we find that their limits are rather different. The first one projects down to this point. The second one projects down to this other point. And you can see that algebraically as well. The first sequence, when you take inner product with u, you get 0, which converges to 0. And the second one converges to 5. So the point is that in some direction, namely in the second one, these sequences, when projected, have different limits. And so therefore, according to this principle, we will require that these two sequences also have different limits. Okay? Okay, so to summarize, how do we answer those two questions? So first of all, which sequences should have limits? Well, in this work, we say that a sequence should have a limit in this enlarged space exactly if that sequence converges in all directions, is the phrase that we use. Meaning that when we compute this limit of these projected values of the sequence inner product with u should exist for every possible vector u. And for the second question, when should two sequences have the same limit? Well, exactly when those two sequences are all directions equivalent is the phrase that we use. Meaning that they have the same limit in every possible direction. So algebraically, it means that when you project the first sequence and take the limit, you get the same thing as for the second sequence. And that's true for every possible vector u. All right, and note importantly that these limits can be in the extended reals, so they can be plus or minus infinity. Okay, so yes?
Sorry, maybe I'm just confused. So, or
Don't apologize, please.
yeah. So it's only depends on direction. It needs to be the same for all options.
No, it has to be the same for every vector u. The vector u is I'm calling it loosely a direction.
I see, but that's
Yeah.
not necessarily the direction of the sequence.
Right, it's not the direction of the sequence. Okay, so like this, the picture is like this, that you're projecting in different directions. So here we project it to the right, and then we project at this diagonal. And you really need, I showed two, but you have to consider it for all possible vectors u.
Right. Okay. Sorry, this was my brain part.
Other questions?
This almost resembles the definition of weak convergence. Was it inspired by that?
It was not inspired by weak convergence, but yes, it's, well, the topology we end up with, it ends up being the weak topology. And so, yeah. I mean, it's similar ideas are used for other compactifications also. It's like stone check compactification. Yeah, so this general approach is not, we're applying known techniques, yes. Yeah, Jamie?
Presumably we're not going to do the thing where we're going to like close any sequence to include its limit, right? So like if something approaches 2 but never reaches 2, right? We're not going to do anything with that, right? Like it will be a sequence that, I'm just thinking, I'll ask you afterwards. I have a question about like, we're adding points to like the range, right? So
We're adding points to the space.
Yeah.
So we're taking Euclidean space,
Yeah.
and we're adding points at infinity.
Yeah.
And then we'll have a notion, then we need to define a topology, which I have not said, which will define a way of, will define what it means to converge. Mm-hmm. Okay, good. Okay, so when we take Euclidean space and we expand it in the way that I described before, using these criteria, that's when we get astral space. So that's what astral space is. And we write astral space like this, so it's Rn with a bar over it. So it's not R bar raised to the nth power. It's not the Cartesian product of R bar. It's Rn with a bar over it. So in one dimension, we're really only adding plus and minus infinity. So one-dimensional astral space is just the same as the extended reals, as we would expect. And before I go on, let me just update our notation a little bit. So I said scalars are italic and vectors are in bold. So astral points, so points in this expanded space, Rn bar, we write bold with bars over them. So X bar, Y bar, and so on. Okay, this way you can tell the type of objects by the font that's used. Okay, so let me mention some topological properties. So I mentioned topology already. I'm not actually going to say what the topology is, but let me say some of the properties of that topology. So the first thing is that astral space is compact. And if you know what compactness is, great. If you don't know what compactness is, I don't have time to explain it, but it's this very powerful mathematical property, and it's especially useful for things like proving convergence of iterative algorithms. It's useful for all kinds of things. Okay, so that's the first property. A second really important property is that every linear function can be extended continuously to astral space. And I'll explain what that means in a little bit more detail a little bit later. But what it means, what it implies, is that anything linear is likely to behave nicely when we extend it to astral space. And that's especially relevant to convex analysis, which is so very much based on things that are linear. And so it means we can generalize kind of obviously linear things like linear maps and hyperplanes and half spaces. But it means we can also nicely generalize things like what it means for a set to be convex or what it means for a function to be convex. And we can extend conjugates, and we can extend the differential theory, so gradients and subgradients and so on. So astral space is mathematically a compactification of Euclidean space. And there are certainly other compactifications that are possible. In the context of convex analysis, what's especially relevant is the cosmic space of Rockefeller and Vetz, which is closely related to the enlarged space of Hansen and Dupin. So the defining feature of astral space is that it has this property that I talked about already, that every linear function has a continuous extension. And among all compactifications that have that property, astral space is the smallest, meaning it adds the fewest points to the space. Okay, so that's what defines astral space. And the last property I wanted to mention is that astral space is not a vector space, and it's not even a metric space. It's not a vector space, and it's not a metric space. Okay, so, but even so, even so, it's got some nice, very nice properties, and it's possible to work with. Yes?
So when are limits of convex functions defined? I'm thinking of the example of the exponential and the squared.
I missed the very first part of your question.
So are limits of convex functions uniquely defined?
Limits of functions.
Convex functions, yeah.
So you mean like where you have a sequence of functions?
Or just like you have your convex function and the minimizers at infinity, is that going to be uniquely defined?
Yes, it will. And I'll get to that. Yeah. Okay, good. Okay, so that brings me to the next part of the talk, which is what are astral points like? What are the points in the space like? So as I said already, the simplest sequence to infinity is a long array from the origin. So a sequence like this that we looked at already, which is just of the form t times v for some fixed vector v. Okay, it just follows a straight line to infinity. And it's possible to show that a sequence like that converges in all directions. It's actually pretty straightforward to show that. And therefore, because it converges in all directions, that means that that sequence has a limit in astral space. And that limit is called an astron. So a point in astral space is just called an astral point. And an astron is a special kind of astral point. And we use this notation to denote an astron, this omega v. So omega basically stands for plus infinity. And so it's like we're taking a scalar product of plus infinity with v, and is what this notation is suggesting. And again, omega v is just the limit of such a sequence like this. All right? And astrons are really important because they turn out to be the building blocks of all astral points. So let me explain what I mean by that. So to explain it, let's look at another example. Okay, a little bit more interesting example. So suppose we pick three vectors, v1, v2, and q. And we consider a sequence like this. So t squared times v1 plus t times v2 plus q. And that sequence, it's basically just following a parabola to infinity, as shown here, where the parabola starts at q. And intuitively, what's happening with a sequence like this is that it's converging to infinity most strongly in the direction of v1, right? Because this t squared overpowers everything else. But it also has secondary convergence to infinity in the direction of v2. And then it also has like this finite shift or offset by q. So it's straightforward to show that a sequence like this converges in all directions again. So it has some astral limit. that I'll call x bar. And it turns out that we can write that point x bar in a very particular form. So we can write that limit x bar like this. Okay, so q is just this vector q. And omega v1 and omega v2, those are astrons, the astrons associated with v1 and v2. And then we have this funny looking plus sign, this dot plus. So that operation that connects them is called leftward addition. And unfortunately, I don't have time to explain leftward addition. It's not particularly complicated, but I just don't have time to explain it. But it's similar in many ways to vector addition, but it lacks other properties of vector addition. So in particular, it's not commutative. It's not a commutative operation. Instead, it gives a kind of dominance to the term on the left, which again, you have to kind of take my word for it because I don't have time to explain it. But what it's doing is it's capturing, in a case like this, it's capturing the fact that this sequence has two different directions in which it's converging to infinity, and the first direction is much stronger than the second direction. The convergence in the direction of v1 is much stronger than v2, and that's being captured by this leftward addition. Yeah?
Okay, it doesn't feel like the degree of a polynomial is reflected on this addition. Is there a reason why?
Oh, yeah, right, because you mean the fact that it's t squared and t, yes. So it's only capturing which, the relative strength of the, of how fast you're going to infinity in each of these directions. So if you change this to like t to the 1 million and change this to square root of t, you would get the same limit. So it's not sensitive to the relative rate, the rate. It's just which one is going faster than the other. Good point, yeah.
Does there have to be one that like goes the fastest? Like how do you know that you can order it always to them?
Oh, well, if they're going at the same rate, you mean like if you had t times v1 instead of if they were both t?
Maybe you have like f of tv1 plus g of tv2, and then they somehow different rates at different points.
Well, yeah, I guess that's a little too abstract to answer in general. But like if they're you know, if they're, let me do one more slide and then, so basically the short answer is if it has an astral limit, then it's always going to have an ordering of directions like this. Okay, and I'll explain that on the next slide. Yeah.
In the interest of time, maybe we'll save the questions for the question and answer at the end.
Okay, unless there's like quick clarification or something. Okay, am I going too slow? Oh shoot, I am going, oh geez. Okay. Sorry, okay. Okay, so in general, it turns out that every astral point can be written in this kind of form. It turns out that every astral point can be written like this as a leftward sum of astrons together with a finite point over here. Okay, and what's more, we can also require in that representation that these vectors v1 through vk are orthonormal, and also that this vector q is orthogonal to all the vi's. Okay, so every astral point can be put in this form, and that also implies that sequences which converge to astral points, which are convergent, will have this ordering of in the directions in which they're converging to infinity. But it might be more than two. It might be like k. Okay, and then we can define the astral rank. So the astral rank of a point, of an astral point x bar is just this number k. So it's just the number of astrons in that point's representation. So if the astral rank is 0, then you have a sum of 0 astrons. So that just means the point is actually a point in Rn. So the points in Rn itself have astral rank 0. And the points with astral rank 1 are the points which are the limit of a sequence along a half line. Okay, so let me move on to talking about how to extend functions to astral space. Okay, so suppose we're given a convex function f, and we want to extend it to astral space. And now we're going to use this notation f bar for its extension to astral space. So f is defined on Euclidean space, f bar is defined on astral space. So how should we define it? Well, let's go back to the example of the exponential function. Okay, so here's the exponential function, which we already talked about extending to the extended reals, which is the same as one-dimensional astral space. But now we're using this notation f bar for its extension. Okay, and before we said that we want to define that extension at the point minus infinity to be 0. Why? Well, because if you have any sequence which converges to minus infinity, the function values are converging to 0. So this is like the only reasonable way of defining this extension at minus infinity. And the same thing for at plus infinity. Okay, it's the only way to extend to the extended reals in a continuous way. So in the general case, we're given a convex function. We want to define its extension. We're given an astral point x bar. How should we define that extension at x bar? Well, suppose we're in that case like we just talked about for the exponential function. Suppose it happens to be the case that the limit of those function values exist and they are the same for every sequence of points converging to that astral point x bar that we care about. So in that case, the only reasonable way of defining the extension at x bar is to be that limit, which is the same for any and every sequence converging to that particular astral point. Okay, and if that holds for every astral point, then f bar will be the unique continuous extension of the function f to astral space. So, for instance, suppose f is a linear function. Suppose f is equal to x dot u for some fixed vector u. Well, if we have a sequence that converges to x bar, then what we're interested in is the limit of these function values on that sequence. Well, those function is just equal to x dot u, inner product with u, right? So this limit of f is just the limit of these inner products. And the limit of these inner products exists, and it's the same for every sequence that converges to x bar, because that's exactly how we defined astral space. We constructed astral space so that it would have exactly that property.
Is that limit finite?
It doesn't have to be finite, no. Yeah, so the limits are in the extended reals. Correct. Okay, so therefore, this function f has a continuous extension f bar. And in general, every linear function can be continuously extended to astral space, as I said before, just because of how we constructed the space. Okay, so returning to that diagonal valley example that we had before, so it's possible to show that this function also extends continuously to two-dimensional astral space. So before we saw that f is minimized by a sequence like this of the form t times v, where in that case v was this pair 1, 1. So now in astral terms, we can say that that sequence converges to an astron, omega v, and that f bar, the extension of f, is minimized at that astron omega v. And because this function, because f bar is continuous, this function f will also be minimized by any other sequence that happens to converge to omega v. Okay, so far I was imagining that f has a continuous extension, which is kind of an interesting special case. In general, it might not have a continuous extension. Okay, so in the continuous case, we defined the extension at x bar to be this limit, which is the same for all sequences converging to x bar. In the general case, we do the same thing, but we take it, because these limit values might differ for different sequences, we take its smallest possible value, the minimum of these limits. And without worrying too much about the definition, just some properties, useful properties of an extension when you define it that way. So first of all, that extension must attain its minimizer in astral space. So whereas the original function might not attain its minimum, when we extend it like this, it always attains its minimizer. And a point x bar minimizes f bar if and only if there's some sequence that converges to it which minimizes f. All right, so just quickly return to this two-speed exponential example. Okay, so we saw before that this function is minimized by a sequence like this of the form t comma t squared, which we can write as t squared times e2 plus t times e1, where e1 and e2 are the standard basis vectors. And we've seen sequences like this already, and we saw that they converge to a point which is a leftward sum of Astrons. Okay, so we can write down what its minimizer is. And f bar is minimized by that astral point x bar, which you'll notice has astral rank 2, and it has no other minimizers. So in particular, it doesn't have any minimizers of astral rank 1, so it cannot be minimized along a straight line. Okay, and f bar, it turns out, is not continuous at this point x bar. You can show with an example. And so that shows that even if the function is continuous, even if f is continuous, its extension might not be. Okay, so let me quickly talk about the last part. Okay, so in standard convex analysis, if the gradient of a function at a point is equal to 0, then that point minimizes the function f. But now suppose instead that we have a sequence of points, maybe computed by an algorithm, and on that sequence of points, the gradient is converging to 0. So if you have a sequence on which the gradients are converging to 0, does that mean the function values have to be converging to the minimum of the function f? So the answer is no. So here's an example. You can basically ignore the bottom part. We really mainly care about the top case. The function is basically x1 squared over x2. But this function is convex and continuous and finite and not negative, continuously differentiable everywhere we care about. Okay, now let's look at a sequence like this, t squared comma t cubed. You can just compute the gradients using ordinary calculus, and those gradients are converging to 0. But the function values are converging to plus infinity. So the gradients are going to 0, but the function values are going as far from the minimum possible value as possible. Okay, so far this has nothing to do with astral space. But let's think about it in terms of astral space. Okay, so again, here's the sequence, t, which I'm writing in terms of these standard basis vectors, e1 and e2. And so this sequence converges again to a leftward sum of Astrons. And it turns out that f bar is not continuous at this particular astral point. And it turns out that that's not a coincidence, because if we assume continuity, if we know that it's continuous at a point, then we do have to get convergence to the minimum. So this is the kind of theorem we can prove. So if the gradients are converging to 0, and if the sequence, and if we add the assumption that the sequence is converging to a point, an astral point, where its extension is continuous, so we add this continuity assumption, then the function values have to converge to their minimum. Okay, so this is kind of revealing, using Astral techniques to reveal some kind of structure and regularity that's not otherwise apparent. And we can use that to prove the convergence of a whole bunch of algorithms, you know, gradient descent, coordinate descent, steepest descent, applied to things like logistic regression, boosting, maximum likelihood. It turns out that the convex functions associated with all these problems all have continuous extensions, so we can apply this theorem to prove convergence. And the important thing is that we're not requiring that the function have a finite minimizer. So these are just the ordinary algorithms operating in Euclidean space, like gradient descent. But we're using Astral methods to prove convergence, and in particular, we're relying on Astral continuity properties, since otherwise the results wouldn't hold. Okay, so that brings me to the end. So I tried to give you a taste of Astral space. And again, we're trying to expand the foundations of convex analysis. We hope that this will help to make for simpler proofs of convergence, for instance. And there's a lot more that was not covered in this talk. So again, this is going to be published as a book. And this is the URL if you want to check it out. It's only 600 pages. Okay.
Thank you.
Thanks.